Well, welcome back, everyone. Before I finish my lectures on this topic of effect modification, I want to try to compare it to what we said about confounding and bring in some analogies, but really try to stress the differences between these two concepts. So here's the take-home message, that the big picture that I want you to go home with, that the concept of confounding, last week's topic, and the concept of effect modification, what we've been talking about in this lecture, are entirely independent concepts. They have nothing to do with one another. You could have a study where you both have a factor that's both a confounder and an effect modifier, or it could be neither a confounder nor an effect modifier, or it could be just a confounder and not an effect modifier, or just an effect modifier and not being a confounder. They have nothing to do with each other. Confounding is a problem. It's giving us the wrong answer. We have to control for it. We saw in the crude analysis we were working at last week that if you compare all the smokers in the Framingham data set to all the non-smokers, the risk ratio for dying in 24 years of follow-up is around 1.07. But after you control for age, that risk ratio changes to about 1.4. Age is a confounder. So confounding is a problem. It's something you have to avoid by randomization or restriction, or maybe by matching in cohort studies, or more formally, you adjust for it in the analysis. On the other hand, effect modification is truth. Think of personalized medicine. It may well be that this treatment works very good for this type of person and works entirely differently in another type of person. Those are true statements. They're not wrong answers. They're not confounded answers. So if you have an effect modifier, if you want to display different results for different types of people. So conceptually they have different implications, ramifications. One's a problem that has to be avoided. The other one is something you might want to show. It's reflecting truth. The reason they're confused together is that both of them involve or are detected so far in this class by looking at stratification. And that's why I think people might get the topic of confounding is somehow confused with the topic of effect modification, because they both involve doing similar calculations in a data set. But even though they both involve stratification, they look at different parts of the stratified analysis to reach their conclusions. And I'm just going to sketch out those different parts in a couple of slides. Let's suppose you have some data and you build a crude analysis looking at the association between your exposure and your outcome, combining everybody into one table. It gives you a crude measure of association, like a risk ratio. It might be confounded. So let's suppose you stratify your data set into males and to females, because you suspect age might be a confounder, or you suspect that age might be an effect modifier. The only way you're going to be able to answer the questions, is age a confounder or is age an effect modifier, from what we've taught you so far in this class, is by stratified analysis. So the next step is the same. Regardless whether you're looking at confounding or effect modification, you break your data into subgroups. One subgroup just contains men, and one subgroup just contains women. And what we do is we could measure separate values for your measure of association, say your risk ratio, just among men. Let's call that risk ratio sub 1, and the other one, risk ratio sub 2, is the value we get among females. Last week, we talked about Mantel-Hansel. We talked about weighting those two separate sex-specific results into one number using Mantel-Hansel's formula. So using Mantel-Hansel's formula, you can come up with an adjusted risk ratio, which is an average of the risk ratio you see among females and the risk ratios you see among men, knowing that both of those risk ratios are free of confounding. So here's a question. On this slide, there are 3 risk ratios. One based on just men, one based on just women, one based on everyone together. Which of them, if any, can be confounded by sex? So let's think about a confounding question first. This risk ratio based just on men cannot be confounded by sex. Everyone's a male. You're comparing male smokers to male non-smokers. This risk ratio sub 2, just on the females, cannot be confounded by sex. Everyone's a woman. You're comparing female smokers to female non-smokers. The only place you could have confounding in this data set, or in this slide, is up here in the crude table. Only the risk ratio that combines everyone into one table could show any confounding by sex. That's the first point to keep in mind. Well, how do we look for evidence of confounding by sex? Well, we display our data set like this, but what we do to detect or to find evidence of confounding, we compare the one value that could be confounded, the crude risk ratio, to the value that we know is free of confounded, the adjusted risk ratio. So answering the question, is there evidence of confounding by sex, involves comparing something in the top table, the crude risk ratio, to something that we had on average in the bottom table, the adjusted risk ratio. But now if we answer an entirely different question, is there evidence that sex is an effect modifier? This top table, this crude risk ratio, doesn't tell you anything about the risk ratio reflecting the effective exposure for men being the same or different as the risk ratio for the effect of the exposure being the same or different among women. The top table tells you no information whatsoever about effect modification. Just showing you that top table doesn't allow you to answer the question, is sex an effect modifier? It's the only table that could have confounding, but it's also the table that has no information in it at all to answer the question whether you have effect modification. To answer the question about effect modification, you ignore the top table altogether. You don't even care whether it's confounded or not confounded. It doesn't help you to answer the question whether you have effect modification. You want to compare the effect of the exposure among one group of people, the men, to the effect of the exposure among another group of people, the women. So it doesn't involve the crude table. It doesn't even involve that adjusted risk ratio that you calculated using Mantel-Hansel's formula. It doesn't involve any of the components you use to answer the question about confounding. So they're entirely different concepts, and the way we find evidence for each of them, although it involves stratification, involves different components of the stratified analysis. That's the point I wanted to stress. Okay, that's all I wanted to say about effect modification. As I say, there'll be a stated demonstration that'll take you through the exercise of looking to see if there's evidence of effect modification by using those tests of significance that I mentioned, the Breslow Day test. It'll talk about ways of displaying your results using standardization. So you'll get more experience by looking in the stated demos. But that's what I wanted to say about effect modification and matching. Next week, I want to return to the topic of confounding. I want to talk about regression models, something that Marcello is introducing in his biostatistics lectures right now. And then I want to introduce this notion of propensity scores also, that I referred to briefly in the previous lectures. So I'll see you then. Have a good time.